Well, hello everybody. Welcome back to the bench and welcome to our next project. Yes, you will have to try to hold back the tears as we go through this one. So what we have in front of us is a McIntosh MC2100, or what remains of a McIntosh MC2100. And as I go through this, you'll kind of get the idea of why I'm saying all this. So first of all, you can see how just bad the condition of everything is. I mean, there's rust pitting all over everything. The transformers are just gross on the outside. There's transistors missing. Somebody put this GE add-on snap-in, replacement plug on the end of the cord. The fuse cap is missing. It just gets worse and worse. Transistors missing. And yes, when I acquired this, the main problem is the driver boards are both gone. There is no driver board. I picked this thing up for next to nothing. I think somebody had purchased it in the hopes of rebuilding it or doing something and realized what a basket case it was, and just wanted to just get rid of it and get it out away from them. And I took it in, and I don't really know right now what all is going to be required, because there's just so much wrong with it. The more I dig through it, the more stuff I find. But the lettering is still there somewhat, although the chrome is badly, has surface rust on it. But it's kind of there. And you can see transistors missing. There's all kinds of screws missing. Some of the screws are the correct ones. Some of them are wood screws that have been driven through here. You can kind of see them in there. These controls feel really bad. The switch feels really gritty and gross. We don't know when the last time this thing ever worked was, but I intend to do my best to at least get it to work. Now, let's look underneath here. Flipping it over, the bottom cover is pretty bad. It's all scratched and rusted. The feet are missing. All the screws were missing. This is how it arrived. It just kind of arrived in a cardboard box wrapped up with some plastic and paper, so it's been rattling around in a box. And you know how, any of you who've ever picked one of these up, you know how heavy they are. So it's a miracle that this thing even made it without being totally smashed. So I was kind of surprised at that, but I'm glad. So we take this off, and the little bit of good news is at least this board is here along with a ladybug. Yeah. That ladybug looks pretty old. Stuck in a spider web. Nice. See that? Good grief. Say hello to the camera. Right there. Anyway, flipping this around, most of this under here, at just the first quick glimpse, looks like it's probably mostly original. Doesn't look like a whole lot of work's been done underneath, but who knows? This thing's so... ugh. But at least the underneath is here, and more importantly, the transformers are all here. Now, I really only care about one thing at this point in time, and that is, are the transformers good? If the transformers are good, we're going to go through... I'm not going to call this a restoration because there's not enough of it here, I don't think. I guess I could restore it, but I'll tell you why I'm not going to call it a restoration here in a minute. But what we want to do is we want to check these capacitors. Of course, they're replaceable, but I would love to use the originals if we can, if they're still good. And I would like to make sure that the transformers, I would think that probably those autoformers are good because it'd be kind of hard to damage them. But the power transformer is another story. We want to make sure that it's good. So we're going to test that, and then we're going to make our assessment from there. So just taking a quick look at the schematic here, we can see that it's a very simple power supply. You have your mains input coming straight in, going through either 1 or 2 fuses depending upon the model number, and our serial number on our unit is, I'll show you, and I can show you that on the chassis later, but it's serial number 93W07. And if we look at that, that means that this fuse does not exist on our serial number. So there's a single fuse going through 2 thermistors, and those thermistors are kind of like inrush current limiting resistors is what they do. So in other words, when these are first cold, when you first plug this in, these are cold and they have a low resistance. Or I'm sorry, they have a higher resistance, and not super high, but they do have a higher resistance. We can measure them and see what they are. And then as current begins to flow through them, they heat up, and as they heat up, the resistance will drop, and it'll drop very, very low. And the purpose for that is so you don't blow a fuse when those gigantic capacitors in here, C201 and 202, are charging up. So instead of having a resistor that has a timed relay that shorts the resistor out, which we call the soft start circuit, this is their way of handling soft start to charge the capacitors more slowly and not cause a great big inrush of current. So it's pretty cool. Now, down here you have a couple of thermal breakers, and those are connected to the heat sinks of the output transistors for the right and left channel. So if either channel overheats, it just opens up that little circuit, which cuts power to the machine. So that's all that is. So it's a very simple circuit. We look at our output. We have one winding here that is for the main high currents DC rail supply for your outputs, and it's your plus and minus 35 volts, and that's where you have these great big 39,000 microfarad at 40 volt capacitors. Very impressive. And those are what actually and then you have this 1K 2-watt resistor to bleed these off when you turn the amplifier off. You notice you don't even have a power switch on this, so this is intended to be plugged into your preamp, whatever it is, and the switched outlet of your preamp actually handles the amplifier. So then you have this other power supply, which is a higher voltage one, and this runs the rest of the circuitry in the amplifier. So very simple power supply, but it does the job, as anybody who's ever heard one of these can test. You know, it works pretty well. So really all we're going to do right now is we're going to statically check all these components. We're going to check our windings and make sure that they're good. And right now, when we wire it for American Power for 125 volt operation, then these are going to be in parallel. So the 2 windings, you could see this is wired for 125 volt use. If you wanted European Power, then you would wire these in series. And that's how this works. So this should be wired this way. And these 2 thermistors, we'll take a look at them and we'll measure them, make sure they have continuity, make sure we have a good winding here, and then we'll apply power through a dim bulb tester and just check the outputs of these windings to make sure we have voltage. If this transformer is bad, this is the end of the project. I'm probably not going to go any further with it, and this will be sold as parts. So hopefully we have something to work with. We're now zoomed in on our input, and you can see your mains cord down here in the bottom of the screen coming in, and it goes across. I'll show you. It goes across this little power outlet, and then from there it goes through the fuse socket, and from the fuse holder it splits off into these two thermistors, because these are wired in parallel for 125 volt use, and then they go to the one end of each winding, and then the other end goes through these thermal circuit breakers and goes to the other two ends of the windings. So looking in the actual amplifier, we can see our mains coming in, and we can see this end going through this wire to the fuse holder, and from the fuse holder down to these two thermistors that are tied together, and then each one goes to the tops of the two windings of the primaries. So we should be able to measure from here to here. Let's see if I can get a good reading through all this tarnish, and that's good. And then of course the fuse is missing from the socket, so we'll skip over to here, and here to here everything's good. And then if we go from here to here, we should read low ohms. It shouldn't be 0 though, but it should be just a couple of ohms, and you can see we have that there if I move my hand. And this one should be about the same, and it is. And then what's going to happen is when we apply power to this, if this were under current, like when it's charging up the capacitors, these will heat up, and as they heat up, that resistance will drop down from that 3 or 4 ohms or whatever it is down to about 1 ohm or even less. So that's what, and then it'll stay at that as long as this amplifier is on. These will stay at an ambient temperature, and they'll regulate that inrush current. Now, a lot of people might say that that's a bad thing. When you put something in the line like that, you're limiting for the transient peaks, but you have to understand that's why they're using such large capacitors in here. With something as small as a 100 watt per channel amplifier, you're never going to get the current, any kind of current draw at that amperage that this can't replenish those big capacitors. So I hope that kind of explains it. So it mathematically and physically it works. Now, if I go from these over to the other side, we should be able to read a continuity across the windings. So the first thing we're going to look at is we're going to look at this one side over to where they tie in. I should have something, and there it is. Sorry. So it's low ohms. Again, this primary is low impedance, very low resistance because of the thickness of the wire. And if I go to the other side, same thing. And where I'm checking here, if I move you over, you can just kind of see it. You have the other ends of the windings coming out here. Here they are. And they go around and they go up to this terminal here, and they go to a terminal over here somewhere. And you can see here's your one thermal cutout breaker, and here's the other thermal cutout breaker. And then they go onto these two wires that are right here, which are coming from the other primary. So they're tied together, and you can see that. So good news, the primary of this transformer is good. So it should be able to power up. Now we can also measure the secondaries, but I'm pretty sure that they're going to be okay. And I just wanted to make sure we could apply power to this, and then we'll just check for some voltage. Alright, taking the 30,000 foot view here, I have disconnected the power output to the plus and minus DC rail going out to the output section and the driver section, because that's in an unknown state. And although I have left it connected over here, there's really this doesn't look like we're going to have any problems. It's all kind of intact. And I've removed the primary wires from the 90 volt supply. And you can see them right here floating in midair. So we're going to first measure over here. I left these bleeder resistors in, so it'll bleed these caps back off. But we're going to plug this thing into power, and we're just going to kind of jumper it right across there and put it through a dim bulb, obviously, for current limiting. And we're going to check it, and we're going to see where we are. We now have our mains connected through our dim bulb tester. Let's just plug it in now and see what it does. And the dim bulb lit up real bright, and then it went very, very dim, almost completely out now. So if we measure here, we have negative 35 volts, and we have positive 36 volts. And again, we have the dim bulb in line, so that's right about where we should be. And remember, this is totally unloaded. There's no, other than that 1K resistor, that's very good. If we unplug it, it should start bleeding off, and it is. Same on this side. Okay, that's good. So now let's look at so we know that our windings are good on the secondary for that, for the high current supply. Now let's check our 90 volt, and we're just going to check it for AC power. We now have the meter switched over to AC, and we have our meter probes connected to the secondary, which is disconnected from the power supply, as you can see. So we should see some AC voltage there now. Let's see. And there you go. And remember, we're not reading with respect to the center tap, so that's about right. You can see it's about 170 volts AC RMS. And why is it not 90? Well, because I'm not reading from here to here, because this is a half-wave rectifier. We are reading from here to here, so we're reading the entire winding from end to end. So that's going to be double what it should be from the center tap to either end, if that makes sense. So the good news is we have a good power supply and a good transformer. We have something to work with. And we don't have any shorted filter capacitors. At least they're not shorted, because they charged up and the dim bulb tester went completely dim. So even though the capacitors may not have the highest ESR or anything, or the lowest ESR, we don't know, maybe it does. We know that the capacitors are at least not shorted or damaged. So this project's good to go on with. Well, just out of curiosity, let's see what these caps look like. I bet they're good. We're going to connect to ground, and we're going to use our little stinger cable, and I've shown this many times in other videos. We're just going to verify that these are shorted out, or I mean these are discharged fully. So there's the minus there, minus there. So we know we're good. So it's all discharged. Now let's take our ESR meter and just do a quick check and see how it is. That one's good. And let's see, let's make sure I can, there we go. Look at that, the ESR is great on those. So there's nothing wrong with these caps. Once I get the probes on there right. So I don't even see a need to replace these big filter caps. They're perfect. If there was any leakage at all, this is a 100 kilohertz test. It would be, it would show up on this. This is actually a pretty good test device. The more I use it, the more I'm starting to like it. And it puts low voltage on the capacitors. This doesn't really work with small capacitors like little the wax capacitors or the little mica capacitors or whatever. This is really designed for big electrolytics like this. This is probably one of the best tests or most accurate that I've used so far. It really works. So anyway, we got good filters. So now let's talk about a game plan. Now for the game plan. So there's many different ways we can go with this, and this is just going to be my way of doing it, but there is no right or wrong. There's all kinds of different opinions out there. I'm sure there's going to be, but here's what I want to do. Because of the age of this thing, how bad condition it is, I'm not going to go out and turn it into an original MC2100. Although when we rebuild this, I want it to maintain the same character that an MC2100 amplifier has. So what do I mean by that? Well, these driver boards, you can still purchase them. The last I checked, you can still purchase them from McIntosh. They're not cheap, but you can get them. Fully populated, updated boards with modern components on them, but faithful to the original design. There's also at least one other company that builds an aftermarket replacement driver board for these, but I really don't want to do that. I want to design and build my own driver boards for these, and really it's for the challenge. Again, this is a hobby. I'm going to think about what transistors we're going to use on the outputs here. There's lots of options for that, and some update things where maybe we can replace these terminal strips, maybe we won't. I'm not sure. I may just leave them and just clean them. I'll take these 1/4-inch phone jacks out and replace them with modern RCA good quality input jacks. We may change these attenuators so that they're a little bit better condition, because these ones may or may not be good. We'll check them, and we'll do a general cosmetic cleanup. Now, how far I'm going to take that, I don't know yet. I don't know if I want to send this chassis out, strip it down to just a raw chassis and send it out and have it re-chromed, and then we'll have to do something with the lettering, or if I just want to leave it as is and just clean it up as best as possible. Again, I don't know. The transformers, if I can get these labels off, I'm probably going to repaint them because they're just so bad, and I don't want the case to rust on them. I'm more concerned about preserving it than I am about keeping the finish original. I'm not a person that's into patina and that sort of thing. Some people are, but I'd rather it be all cleaned up. So lots of things, lots of decisions. What we're going to do with these driver boards is going to be my first challenge and the first thing that I'm going to think about. And until then, that's going to be it for this video. And as we progress through this, we'll just keep releasing new videos on it, and we'll watch it evolve with time. So again, I thank you all for watching. I thank you for all your wonderful comments, and I wish you all peace, joy, happiness, and good health in your lives. And well, we'll be back soon. Take care for now. Bye-bye.